Hello.
Hello, everyone.
Hello, everyone.
Hello.
Okay, hi everyone. Thanks a lot for joining us. Thanks a lot for joining the workshop on Frontier AI in Cybersecurity, Risks and Opportunities. So now we'll start the workshop. So first, I will give a quick opening remark. My name is Dong Song. I'm a professor in computer science at UC Berkeley and also a co-director of the Berkeley Center for Responsible Decentralized Intelligence. And it is great to welcome everyone to the workshop. And the workshop is co-organized by the Berkeley Center for Responsible Decentralized Intelligence, RDI, and also Schmidt Sciences. So we are all excited about the fast advancements in frontier AI. The frontier AI capabilities has been increasing really fast. And also this year is called the year of agents. And we've seen an really impressive explosion of AI agent development as well. And at the same time, we also need to be aware of different types of risks as well. In particular, I do personally believe that cybersecurity will be one of the biggest AI risk domains for a number of reasons. Today, attackers have diverse incentives for attacks, and today attacks are already causing huge damages. And increased AI capabilities can significantly reduce attack costs and increase attack scale. And cyber attacks and defenses are complex. So for example, for a successful cyber attack, oftentimes it goes through multiple stages in the kill chain. And a key question is, how will frontier AI change the landscape of cybersecurity? Given that AI is a dual-use technology, it can help both the attacker side and the defender side. So a key question is, who will AI help more, attackers or defenders? And why are we hosting the workshop now? So from what we have seen, AI agents are now reaching a breakthrough moment in cybersecurity. So for example, from our recent work, such as benchmarks, like CyberGym and Bounty Bench, and also together with other results, for example, from recent results from the AICC Cyber Challenge, we are seeing the rapid advancement of AI capabilities in cybersecurity and seeing that AI today can meaningfully support many different types of real-world cybersecurity tasks. Here is just one example of our recent work, CyberGym, which develops a new benchmark that includes close to 200 large-scale, widely distributed open source software. And this open source software contains over 1,500 previously discovered vulnerabilities. And we task AI agents with two main tasks. One is to try to detect these previously known vulnerabilities. And the other task is to identify previously unknown vulnerabilities, also called 0 days. So from the CyberGym benchmark and evaluation, it demonstrates that frontier AI's capabilities in cybersecurity is increasing drastically, especially with the most recent model releases. For example, Sonnet 4.5, the AI agents can identify close to 30% of previously known vulnerabilities in the benchmark, which is single trial. And also our agents have been able to identify 35 0 days in these large-scale, widely distributed open source software. A number of CVEs have been issued from our discovery 0 days as well, and also developers have patched a number of these vulnerabilities also. And also CyberGym has been included in the system card for the most recent model release, Sonnet 4.5, from Anthropic. And Anthropic's work also shows that as they increase the budget for agents, this also allows the agents to significantly increase the vulnerability reproduction and the discovery success rate. When they increased the trial to 30 trials instead of a single trial in the CyberGym benchmark, the agents were able to actually identify close to 67% of previously known vulnerabilities, and also discovered significantly more new vulnerabilities as well. So all these recent findings demonstrate that AI capabilities in cybersecurity is increasing drastically. So this poses a number of key questions. So first, how is frontier AI is being applied across different stages of the cyber security landscape, including both the attack and defense side? Second, what lessons can we draw from real-world benchmarks and deployments today? And more importantly, what milestones or breakthroughs will signal that the AI systems will substantially change the cybersecurity landscape and the balance between cyber offense and cyber defense? And how would we together prepare for these tipping points? And more specifically, what concrete steps should stakeholders take, both for near-term and longer-term, to build resilience, close the evaluation gaps, and ensure safe and beneficial uses of frontier AI in cybersecurity? And finally, how can academia, industry, civil society, and government together to work together to better coordinate, to anticipate risks, and leverage the opportunities to really build more resilient society to enable us to benefit from frontier AI while at the same time mitigate risks in cybersecurity. So with that, we'll welcome everyone to join the workshop today. We are really glad to see that about the huge excitement about this workshop and the importance of this topic. So we have over 2,000 registered attendees for this workshop. And in this workshop, we will hear presentations from AICC winning teams, leading researchers from Frontier AI Labs, academia, and also leading tech and security companies and governments as well. And our workshop has two parts. Part one is today, and part two was originally designed, planned to be on November 12th, but due to government shutdown, a number of speakers are impacted for the part two dates, and we'll announce the new part two dates after the government reopens. With that, thanks for everyone, and hope everyone enjoys the workshop.
Okay, I think I need to jump in. Thanks, Don, for the opening remark. I'm Wenbo. I will be the moderator for session one, which is AICC. A little bit of background, what is AICC? It's the cyber challenge, grand challenge that hosted by DARPA. It's been hosted for 2 years, since 2023, and then the first year is from like the initial phase to the semifinal, and the second year is from semifinal to final. From semifinal to final, there are 7 teams competing in the final for a year. In the competition, the team need to build the AI-driven cyber rating system that automatically identify and patch vulnerability in real-world softwares. Today, we are very happy to have the team lead and the core member from the top 3 teams, which give us presentation about what they build and share their experience. We'll start from the winning team, Team Atlanta. Very happy to have Professor Tae-Soo Kim from Georgia Tech. We also the leader of Team Atlanta share with us the experience and the cyber rating system they build. Yeah, thanks.
Okay, can you see my screen?
Yes.
Okay, this is Tae-Soo Kim. I'm professor at Georgia Tech and VP at Samsung Research. Today, I'm going to tell you about hyperscale bug finding and fixing in the context of DARPA AICC and our team, the Team Atlanta. My research area in traditional security area, security research. For example, we are doing automatic bug findings and also write exploit against them. But lately, all the research that we are doing is extended by LLM. Even writing exploitations, we heavily leverage LLM in terms of synthesizing exploit primitives to achieve remote code executions against target software. We are very much grounded teams. We show our capability of writing exploit and defending through various competitions, such as DEFCON CTF. We also won phone-to-one competition in a way that we can demonstrate remote code executions against Apple Safari and macOS in the past. Unfortunately, though, I'm far from AI persons. I hope that today's takeout from my talk is all about a security expert's take on LLM to solve domain-specific problems and how powerful it is to leverage AI when solving your security problems in your hand. But in the context of DARPA AICC, DARPA has been organizing lots of grand challenges before to address societal problems. Self-driving car, or also known as urban challenge, is pretty well known to public. And there was a humanoid robot competition to develop humanoid robot for the rescue missions. And a few years back, there was competition called Cyber Grand Challenge The goal of CGC is all about creating autonomous agents that can attack by writing exploitation. And each of those grants challenge after several years spark huge industry. For example, it's very common to see Waymo and self-driving car on the road, and we now see huge competitions in robotics, humanoid robot development right now. And after CGC, many of the big companies start adopting fuzzing as a main way to evaluate their security for their software product. DARPA AI Cyber Challenge has been announced in 2023. The aim of the competition is to protect and security critical cyber infrastructure in the United States. So what is AICC? It's a competition to design autonomous systems, or called cyber reasoning system, that can find and patch the vulnerability from the open source project. So one of the core idea of AICC is to scale a traditional software analysis techniques that actually work against the real world software, like Linux kernel, in that scale, so that we can actually find the vulnerability from open source project at the end. This is not just interest from government and academia. It's actually backed by many of AI companies like Anthropic, OpenAI, and Google and Microsoft. And the competition is announced in 2023, but semifinal happened last year, and final happened just a few months ago. And the total amount of stake as a total prize is actually $30 million. Means it's a very serious competition at the end. And semifinal happened a year ago in DEF CON. What's interesting here is that 42 teams competed for the semifinal. Only 7 teams proceed to the final. And we had to analyze Linux kernel and Nginx and Jenkins and SQLite. This is a large scale application with a very limited budget. But what's interesting in this competition is that there are 3 large groups of people competing for semifinal. Some people bringing their AI tool, rooted from AI community. There are another group bringing their PL or software engineering technique. And there are security folks who are experts in security area, but they want to tackle the exact same challenges by bringing their expertise. But at the end, all the 7 teams, and most of the 7 teams are grounded in the security area, which indicates that solving their domain-specific problem by leveraging or recent advances in AI is critically effective at the end. I'd like to give you a little bit of taste of what type of challenges we have to solve in semifinal. This is one of the exemplar challenges from Linux kernel. And in transparent inter-process communication layer, shortly TIPC, when 2 processes are communicating each other, you can create a session key. So when one process initiates the session key, and this is the function that is invoked inside the kernel. And one processor should package everything as one message and send to the other end. So inside the package, there are size fields that represent the total message that you're sending. But at the same time, user can indicate amount of size byte that is related to the data inside. So in other words, the entire allocations happen in the entire message size, but attacker can provide the longer size input for the data they're gonna send inside. This is basically K input. And then they can override beyond the allocated amount, which is a simple out-of-bound memory write happening in this source code. But think about the AI-driven approach, given LLM, how to find such a vulnerability. The Linux kernel alone, we have 30 million lines of code, which is almost impossible to analyze this huge repository by merely tackling everything in a static way. So one of the interesting decisions made by organizer in order to solve this fundamental challenge is to provide harness. You can think of it as a fudging driver that drive the entire interaction or govern the entire interaction from the user input. So this, in the context of the Linux kernel, you can think of a user space program that interact with the Linux kernel with a very explicit step. And your job is to find the bug triggering input that can inject to the user space program and use it to program by interpreting every single field in the data that you provide, and ultimately drive the execution to the buggy locations and trigger the vulnerability at the end. I think I'd like to highlight the differences between tackling this in pure static way and the proof of vulnerability that we care, which is very critical in terms of reachability analysis. If you analyze this entire source code with CodeQL like static analysis tool, and they typically create the big warning against the kmalloc area. So size fields of kmalloc is basically 2 bytes in this case, but unfortunately it's a very error-prone decision because once you allocated 2 bytes size with like 4 byte or 8 byte argument of the kmalloc, is pretty much error-prone in terms of overriding what fields that you're going to override the buffer area after allocation. But in fact, this is actually not related to the bugs that we are analyzing in this source code. The out-of-bound memory override happening in the last line in this code snippet. But most of the static analyzer, we just complain this allocation side with the smaller byte as an argument to the kmalloc. In fact, this also indicates the importance of those criteria in real world. This is coming from one of the open source projects called Curl, and immediately after LLM become popular, and they are effectively DOS by the huge number of bug reports. But according to their practice, because the bug report is so convincing, they have to spend ridiculous amount of time as a developer to understand and validate whether the report is actually correct or not. But at the end, most of their time is actually wasted. So in other words, when you're writing cyber visioning systems, providing the input that actually trigger the vulnerability by solving the reachability problems is significantly important. Probably the most important criteria as a security tool that we care in AICC and general bug finding tool. And what counts for security task in AICC? There are 4 different tasks. One is the proof of vulnerability, basically generate the bug triggering input against the target software. And you also have to fix it by generating patch. And also there's an interesting new security test called Sheriff assessment, meaning that given a report from static analyzer, you have to validate whether you have to decide whether this report is valid or not. And also there's the additional security test that connect the POV to the patch or Sheriff report all together so that you can relate them at the end. And you have to perform 4 different security tests in 2 different modes. You can perform this entire security test on entire repository, it's called full scan mode, or you can apply these 4 different tests in the context of the new commit the developer create. You can think of this actually reflect the real world development paradigm. You create a new patch, say feature patch against the software, and this particular patch likely contains the vulnerability. Instead of scanning the entire repository, we like to perform security tests against those code regions, which called data scan in AICC. Final happened in DEF CON a few months ago, and this is a visualization of the competition. Unlike self-driving car, we don't have many things to visualize. Each of the team is competing in this space and just invoking LLM to the top purple side is the external LLM call. And you can also see the complexity represented as a sphere in the green side. And basically all the sphere is a green circle at the end because of the complexity of the software we analyze. And I'm proud to announce that our team member, Team Atlanta, won the competition. We got $4 million cash prize from the DAPA competition. In total, got $6 million as a whole. But one thing I like to highlight is the actual end scoring. Our system achieved more or less same score than 2 other teams combined. And the rule is pretty interesting. And we also outperform most of the category of the security test. And the rule is pretty simple. They assign a static number to each of the security tasks, but there are interesting accuracy multiplier, meaning that if you make an incorrect judgment call and you make false positive, basically, then your score will be deducted with following this rule. So in terms of accuracy, because of accuracy multiplier, and in fact, this is a realistic challenge from the real world, we make tons of conservative decisions so that we can maintain high accuracy score in this competition. In the final, we analyzed about 28 real-world open source projects that include systemd and crawl and libpng, which actually back everyday software stack that we are using. In total, all the team had to analyze about 70 vulnerability out of 28 repository. We could take about 77% overall team. And out of 54 vulnerability that we identified, we could also fix about 43 vulnerability at the end with a time frame of 45 minutes. What's interesting in the competition, your task is not just finding synthetic benchmark, synthetic bugs in the open source project. You can also find zero-day vulnerability. In fact, in the semifinal, our team is the only team who discovered the zero-day vulnerability in the SQLite. And the final, we discovered about 6 vulnerability by our team and 18 vulnerability total by entire team combined. This is another interesting number that you can see. The total amount of computing spent, with including cloud and LLM resources, our team spent about $360,000 at the end. But if you divide this entire amount that we use in total by the amount of security tests that we have, this is the final number. It means given a random repository, the random open source project in larger scale, this is the amount that we can initiate the pen testing or security auditing. In fact, compared to human auditor, typically takes weeks and months. This is a ridiculously small amount of money. In fact, if I over-exaggerate a little bit, this is the amount of money you can initiate the pen testings against the new code. And now we see huge possibility of automating all this process through AICC. And I'm happy to talk about our approach of Team Atlanta. So when we start this entire competition, when we start preparing this competition, like any other domain experts, we thought LLM is not ready. We started as AI skeptic for reasons. We evaluated all the commodity LLM services outside. Per our evaluation with the benchmark that we designed, none of them actually work properly. And discussion at the time is very primitive. We talk about chain of thought and tree of thought and self-consistency. And even people start discovering some tips, some tricks. Say, hey, if I say I'm going to keep a beat in prompt, and people start realizing that LLM actually respond with the longer response, for example. And there are tons of discussions in primitive level. For example, hey, what's the right way to represent source code inside the prompt? Hey, what's the right way to represent line numbers? Hey, do we need a bracket or semicolons? And what is the right way to generate the patch? And should we just ask to generate the diff? Or what about just to rewrite the entire function so that we can generate the patch at the end? And these are the extremely primitive discussions, but these are very important subject at the time because LLM is merely ready in the time frame. And importantly, context windows seem to be very primitive, and we also realize the fundamental problem. And there is a huge race going on in enlarging the context window at the time. We start seeing some 1 million context window announced by Gemini, but unfortunately, community also realized that even if you have a larger context window, depending on where you locate the needle, and the accuracy of or performance of an entire agent different. So in other words, still it's very critical to maintain the usage of context window small in order to make your agent work effectively at the end. But at the same time, we start seeing some of very huge potential. What's interesting here is that instead of asking LLM to answer the questions that you ask, you can ask LLM to generate the code that can answer the question that you ask. This is a pretty interesting paradigm shift at the time. So that code interpretation become very popular. Now we implement it in our team. We're going to have a proxy layer that implement custom function call that support every single LLM provider, which become more or less obsolete these days. Many of the LLM providers lately provide the native support for the function call and callback and name. We also see a lot of development happening in software agent side. The OpenTavern is very popular, and we heavily leverage those agent architectures in our semifinal. But unfortunately, though, we couldn't fully leverage the LLM breakthrough at the time because we have a limited time and resources. But for the patching, we extended the ADAR and SW agent in a way that we can focus on the specific type of vulnerability in generating patching. For bug finding, we apply the idea of LLM in the loop so that we can replace some of the human efforts by using LLM. For example, when you're generating C to accelerate the performance of fudging, we heavily leverage the LLM for the semifinal. But after semifinal, everything changed. we now see that context window is not the problem anymore because of new technique like summarizations of the chat history, or there are a bunch of compaction techniques. And we can also design the agent in a slightly different way, like sub-agents and multi-agent, in a way that we can effectively utilize the context window in the given commodity LLM. We also start seeing some modern breakthrough in agentic architectures. Like now we have Cloud Code and Codex and Gemini, which happened in the middle of the competition. We actually try to understand their design decisions by reverse engineering and many things behind the scene. We actually adopt many of their design decisions in our final implementation for the final round as well. In Atlanta TRS for the final competition, we adopted LLM everywhere. We have a proxy layer that abstract every single interaction for the supported LLM provider, like Grok, for example, and Gemini and whatnot. Not only that, every single agent that we develop heavily utilize LLM for the bug finding and patch generations and sheriff analysis as well. I'd like to highlight some of the key principles that we adopted when designing CRS. In fact, if you see our CRS design, we have 3 separate agents running concurrently to find the vulnerability. In fact, this is a popular idea in system community called M-versioning for tolerance. And we also made tons of orthogonal design decisions among, so that even if one system fails, then other systems start interacting with the organizer's competition involvement. But at the same time, for C and Java, we still prepare tons of traditional tools, like ensemble fuzzers and concurrent executor and directive fuzzer. These are not as sexy as it sounds for AICC, but we still believe that these are very important subject tools that we have to utilize for better accuracy in bug finding. I'd like to highlight some of the decision here is that when you're generating new input through LLM in the process of fuzzing, the simple idea is that you can ask LLM to generate, or you can ask LLM to mutate given input. But this, because of the property of LLM is extremely slow, the end-to-end latency of LLM takes 30 seconds a minute. It's extremely hard to leverage it. And instead of asking LLM to generate the final input, we ask LLM to generate the code, which can cover the huge amount of input space for the target program. So we can ultimately saturate the fuzzing process through this design decision. And standard fuzzing has 4 different steps. You have a scheduling step that select the input, and you do the mutations and run the fuzzing execution with the mutated input. You're going to update this process. But standard fuzzing is really tailored for specific program languages. And many of those small components require specific extension of the program languages. But in our CRS component called Atlanta Multilang, we actually implemented everything. We abstracted everything with LLM in a way that we can perform fuzzing in language agnostic manner. Our system is actually very complex, but I'd like to highlight one of the components here, what we call testline-based agent. So given a source code, our agent try to create the grammar by starting from the entry point of the harness and navigate the entire source code base. And at the end, it produce the grammar, potentially correct grammar, in a way that instead of doing random mutations against the target program, we can actually respect the type constraint against the input to the target software. The patching agent is all about LLM. We implemented six different agents in our patching agent. We ensemble them together. This idea is pretty interesting because you don't have to develop one agent that works universally well across all these bug types. Instead, you can develop a very specific agent that only works for a certain bug type. But by ensembling them, we can always validate correctness of the patch and produce the valid patch as a whole system. So when we're designing those agents, we actually selected various architectures and diversify the tool calls and adoption of LLM model at the end. I'd like to highlight a little bit of design decision. Martian follow a deterministic workflow. We have a step for localizations by leveraging all these crazy complex tools like symbolic lookup, stack recovery, and we also annotate the circle with the type system. But we have a very simple workflow in a way that we can work effectively. We also have sub-agent-like systems like Cloud Code in a way that main agent can invoke, sub-agent can utilize and interact with them effectively. And multi-agent systems also has a group of team and collaborate together to solve the challenges with the same goal of generating patch. If you combine every agent that we have overall against our benchmark, entire of the system can find the patch against every single benchmark that we design. Our system not just work for synthetic benchmark, we could identify bugs in SQLite and high-profile software in the real. So what's next? We are in the process of standardizing the AI CC benchmark together with the other teams and DARPA organizers. And we're also in the process of generating common interface for patching in CRS. And we're going to launch a new project called OSS CRS together with OpenSSF under Linux Foundation. And most importantly, it's time for real-world AI CC. And one of the first attempts that we made as a team Atlanta is that for visual to apply the AI CC-based system in the context of blockchain and smart contract. 4 visible members in our team from Team Atlanta started a new company called QED Auditing with the aim of implementing hyperscale autonomous auditing and pen testing for Web3. If you're interested in, feel free to contact us at the end of the talk. In fact, if you're wondering about our system decision, everything is open source. We have exhaustive document about our design decisions with 100 pages of technical report. And because of AICC, we truly believe the world change immediately. And we demonstrate that it's possible to automate the process of patch generations in very fast and scalable and cost-effective manner. Thank you.
Okay, thank you so much, Tae-Soo, for the great talk. And also, as you mentioned, thank you so much for open sourcing your report. It's more than 100 pages. It's super detailed. Once it open, we read it as well. So thanks for sharing that with the community. Now let's see if I have some questions from the audience. We can take 1 or 2 questions. Probably I will start. As you mentioned in your talk, like I feel like the multi-agent system is very useful, and the workflow now is kind of like deterministic. Do you see a future where we can maybe open another layer of flexibility to the agent, where we can have ultra-filtered agent that control all the sub-agent and then automatically decide the workflow by itself? Yeah, do you see a future heading towards that path? Is that necessary, or yeah, what's your opinion there?
So in our patching systems, again, we have 6 different agents.
Right.
One of them has a deterministic workflow. The other agents, like they support sub-agent architecture, and they have a very interesting interaction between main agent, and they divide the tasks in a way that they can launch the sub-agent. But we didn't restrict anything that main agent can invoke. And this is not the future architecture. This is one of the agents that we implement as part of entire umbrella project of patch CRS.
Gotcha. Yeah, thank you so much. Yeah, we have some quick questions from audience. The first question is, one of the audience is curious about what is the total cost, not just the hardware, but also time of everybody in the team. It's kind of they're asking not only the kind of cost on the money wise, but also the cost on the team member wise.
I think that's a very important question in terms of how to estimate the amount of development cost to build such a large system. But I like to emphasize that we are rooted in Georgia Tech, meaning that we are pretty much open team. We actually incorporate many of undergrad, many of master's students, many of PhD who express their interest because it's open community for the purpose of education we adopt. So from the outside, it seems like a very large team. We competed in about 30 to 40 people. But if you count how many people actually work in the full time, I'll say 15 is maximum that you can. If you measure very conservatively, I think we can execute the project with maybe less than 10 people very easily if everyone is actually focusing on. But many people jump in and jump out, and many of the students in our team, we have to educate them during the competition. I think it's a little tricky to estimate, unlike maybe theory and trials of bit have more dedicated full-time engineers. I think they can describe those aspects better.
Yeah, exactly. It's also the same for us at Shellfish. We're from UCSB. It's kind of exactly the same situation we are facing as well. Yeah, thank you so much. One last question. It's also an important question, like how does the system work for newer or more niche program language, and how does it generalize? Basically, it's about generalizability of a system beyond like what we provide in SCC.
So Atlantis multiline actually can support multiple different languages.
Right.
If you remember, the AICC actually originally proposed, hey,
Yes.
we have to work on 10 different program languages. That's why we
Exactly.
designed multiline at the beginning of the final. So that, hey, we can now really have to prepare to support those languages. In fact, if you have time, in fact, there are several requests even internally at Samsung, and they request the support for C#, they request support for Rust. In fact, it's not too difficult to provide or extend our multi-length CRS to support those program languages, but with the caveat. So one of the big assumptions in AICC is there is a dependency in harness, meaning that even before initiating an entire project, developers have to express what are the bugs that you care through the harness, the budding driver. But in fact, this is the ongoing work that not just us, that Google also provide automatic budding harness generation, and we're going to work on automatic budding harness generations to make this entire adoption of CRS easier at the end.
Okay, gotcha. Yeah, thank you so much, Tae-Soo, for your talk and for answering all these questions. We will see you again at the panel discussion. Thank you so much. Yeah. Next, we will have Ricardo and Dan from 12 Bits. They end up with a second place in the AICC final, but I remember their CIS was super strong because during the semi-final we have like a lot of badge, like it's real-time badge. 12 Bits get a lot of badge from the semi-final, and then they carry their advantage to the final as well. Without further ado, I give the floor to Ricardo and Dan to introduce their CIS from 12 Bits.
Hey there. So I'll introduce Ricardo and the team a little bit. So one thing that I want to make clear and that I hope people pick up and learn from the TrailBits team is that we had three key principles that we tried to rely on when we built our CRS. The first was that we really prized engineering quality. We tried to build a system that was maintainable after the competition. And in order to do that, we had to build in that those architectural decisions, those code quality decisions, that software development lifecycle process early in the development process so that people could use the code that we released afterward. So that shows up in that today we have a robust system that people can download from GitHub that we are continuing to develop and that we believe will be continuing to be useful far into the future. Second thing is that we did not discard industry standard tools. If we had amazing algorithmic tools, we used them. So our system was very deliberate about the way that we used AI. We didn't throw AI at every single problem. Instead, we found good pairings between state-of-the-art tools and LLMs. And I think the last principle is that it sort of relates to the first. We always intended to open source this. There are a lot of people now that are pursuing venture-backed, startups to build things, to productize these sorts of things. But if you're the kind of person that wants a CRS in-house inside your company with full control over the source code and customizations made to it, then the CRS you probably want to use is the one from TrailBits. So with that in mind, I wanted to introduce Ricardo. He's going to talk. He's a core member of the team. And Ricardo, didn't you at some point study with Don? Am I incorrect?
That's correct. Yes. Yeah. It's a pleasure to be here with her again.
It's all in the family. Yeah, it's great. So Ricardo was a core member of the team and has been with us through this entire journey and will give you a real technical perspective on the system that we built, the design decisions that we made, and why. So very excited to hear more about our team. So take it away, Ricardo.
All right. Can you see my screen well?
Yes.
Okay. So yeah, I'm Riccardo Schirone, security engineer at 12 Bits, and I'm going to talk about our journey to making AICC's Buttercup, our CRS, usable to everyone. Before starting though, a short thank you to the whole team behind Buttercup, including Michael Brown, who was the overall team lead and designer of Buttercup, Ian Smith, co-designer, and also huge thanks to the rest of the team who did great work and worked on different parts of the system. So the idea behind the CC is simple. We already talked about that, so I'm going to skip a little bit on this, but Buttercup is the name of the cyber reasoning system that Trail of Beasts developed. And our journey with it began as part of the small business track a couple of years ago. And then in summer 2024, we placed in the top 7 teams during the semifinals. And this summer at DEF CON, DARPA and DARPA-H released the results of the finals event. And there we discovered Trail of Beasts with its Buttercup CRS, placed second and won $3 million. That was already huge success for us. But what our system was able to achieve, I think, is even more interesting for everyone. So we discovered overall 28 vulnerabilities, and we produced 19 patches in the open source projects we were given. And we are talking about projects like curl, mongoose, systemd, and so on. So projects that contains thousands of lines of code, not toy programs. And these vulnerabilities span 20 different CWE categories, like stack-based buffer overflow, out-of-bound read and write, path traversal, and so on. And all of this was done with almost 90% accuracy, which means that whenever our system submitted a vulnerability or a patch, it was actually a real finding or a correct patch most of the time, and not like a false positive. Last but not least, we had a 68 patching success rate, meaning that 2/3 of the vulnerabilities we discovered, we also correctly patched. And as mentioned before, during AICC, but also for a real tool, it's very important to fix issues at scale. So let's now look in more detail at Buttercup and see how it works. So although originally it was designed as a much more complicated system, it ended up being quite simple at a high level, at least. So the projects or challenges provided as input go through a vulnerability discovery phase that involves a mix of fuzzing and AI to find crashes. And these crashes go to the orchestrator and then our patcher. The patcher's goals is simple. Given a crash, it generates a diff that fixes the crash. And we actually generate a patch only after we see a crash. So we know exactly what we are fixing. We know the input that actually triggers the vulnerability. Both our patcher and our LM-based components for the vulnerability discovery process rely on another component called the program model that analyzes the input challenge and provides tools to extract stuff like function definitions, callers, type uses, and so on. Last, we have the orchestrator that provides proof of vulnerabilities and patches. It interacts with the external environment, like the competition API during AICC, and it deals with the duplicating POVs and patches, a very important task. So let's look a little bit more closely at Buttercup's components. First, we can talk about the program model that uses tree-sitter and code query to parse the project's files and retrieve information like function definitions, callers, callees, types. And these properties are used by the patcher and CGen to navigate the code base. And usually they are provided as tools to an LLM. So by using this static analysis-based approach, we were more confident things would not break. But even if they did, actually, the patcher and CGen had access to other tools, standard LLM tools like cat, grep, and so on, to navigate the code base by themselves and retrieve useful information, even though less efficiently. Then we have our vulnerability discovery component that uses a mix of fuzzing and LLMs to discover crashes. The fuzzer performs traditional coverage-guided fuzzing, and the LLMs are used to expand the fuzzing corpus, and if possible, to find crashes by itself. For the fuzzer part, we relied on libfuzzer and judger, as those were preferred during the competition, but in theory, our architecture could support other kind of fuzzers in parallel. And our CRS spawns several fuzzer bots that periodically run short fuzzing campaigns on a randomly selected harness. So they pick an harness and then start fuzzing that. We also have another service called the merger bot that periodically merges local and remote corpus and keep only inputs that actually improve coverage. And this merging was done to also avoid continuously writing to a remote file system where these corpuses were stored, essentially. Then we have the SIDGen, which is where we actually use the AI in our vulnerability discovery process. It uses LLMs with some tools from the program model to navigate the code base, and also a few extra tools to execute Python code in a sandbox, try proof of vulnerabilities, and so on. And this subcomponent does primarily 3 different kinds of tasks. So we have an init task, an explore task, and the vulnerability discovery task. The init task is used mainly at the beginning of a challenge to bootstrap the fuzzer with some initial seed inputs so that the fuzzer can correctly exercise the harness code. Then we have an explore task that looks at the coverage data, searching for functions that are only partially covered, and it tries to generate some new seeds that explore the uncovered code. In this way, if the fuzzer gets stuck on some part of the code, we rely on LLMs to unblock the fuzzer, essentially. And finally, with the vulnerability discovery task, we try to generate proof of vulnerabilities from start to finish with LLMs, looking for potentially vulnerable functions, retrieving context around those functions, and then generating crashing inputs. Actually, usually these crashing inputs are generated through a Python program, as also was mentioned in the talk before. So during the finals, we had several instances of this component that would periodically pick one of these 3 tasks randomly and try to produce new inputs for an harness. And if we found something great, we would use the crash. Otherwise, inputs were anyway put in the shared fuzzing corpus so that the fuzzer could explore even further and maybe reach a crash starting from one of the new LLM-generated seeds. The next big component of Buttercup is the patcher that was designed as a multi-agent system, actually at the beginning of the semifinals. And it has a few agents that perform different tasks and they have access to slightly different tools. Given a crash and this stack trace as input, we have a security engineer agent that first understands the root cause of the crash, and it explains it to the next agent, the software engineer agent, that determines the best patching strategy at a high level. And then it tries to implement this strategy by modifying some code snippets from the original code base. The patch that is generated is then built, tested, and validated by a quality engineer agent that ensures the patch can actually be built, it fixes the vulnerability that it was supposed to fix, and that it keeps existing functionalities intact. And if anything goes wrong during this pipeline, we move to a separate step called reflection that analyzes the failure, look at all the previous patch attempts, and determines what to do differently to try and regenerate a valid patch. Finally, we have the orchestrator component that organizes the work of all the other components, and it sends and receives messages on various queues, communicates with the external world to accept new tasks, provide vulnerabilities and patches, but it also deals with vulnerabilities and patch deduplication. So you care about vulnerabilities rather than single crashes, right? Because multiple crashes can, of course, be caused by the same underlying vulnerability. And you also want one patch for each vulnerability, not one patch for each crash. So you want a patch that is generic enough to fix all occurrences of a vulnerability. And this deduplication process starts already in the vulnerability discovery component, which has a very basic filtering step that discards crashes based on a crash token that is embedded in the stack trace. Then the rest of the duplication is done in the orchestrator, which performs some heavier processing to group similar crashes even more. First, based on stack trace similarity, essentially, and then based on the patches we generate. So we group together crashes that are fixed by a single patch so that we can bundle multiple crashes and one patch together. And this was important to avoid sending too many crashes and patches to the competition API. So this is how our Buttercup cyber reasoning system works at a high level. But AICC ended this summer, right? So what now? Fortunately, AICC was not the end for Buttercup, because at DEF CON, as it was mentioned by Dan, we released a more streamlined version of our Buttercup system that you can find at this URL. And we kept developing on this actually even before DEF CON, because the original Buttercup was developed under a lot of stress, with tight deadline and with some clear constraints due to the competition, of course. But now we can break free of those constraints and try to make this tool more easily available to everyone and expand its scope and functionalities even further. So one of the very first things we did was coding this simple web UI to ensure that you can keep track of what's happening. Before, you had no way of understanding what was going on without querying hidden REST APIs, looking at the logs. But now with this UI, you can easily see what are the current projects the CRS is working on, which POVs it found. You can submit new tasks just by providing the name of an OSS Files project and its Git URL. And you can check POVs that were discovered. You can download them and reproduce them separately if you want. And you can also approve or reject patches that are generated by the systems. I think this feature is very interesting because during the competition, we had the competition API that was kind of validating the patches, and it was telling us if they were okay or not. But in the real world, you might want to review what Buttercup generates and validate it for yourself. So if the patch is accepted, cool. But if it's rejected, we trigger a new patch request for within the CRS. And this could potentially be expanded even further with some textual form feedback, maybe a natural language explanation of the patch from the CRS as some sort of pull request review process. Another thing we worked on was improving LLM integration. So during the competition, we had a lot of LLM credits. And so having limits or concerns about spend was not a very high priority. But now, however, we do worry more about not spending thousands of dollars while running Buttercup for testing, for example. So you can set up during deployment an LLM budget that can't be surpassed because it's enforced by the light LLM proxy. And moreover, we added support for Gemini, which we didn't have. And we made sure that all components can work with any of the main big LLM providers. And it's enough to have one of the API keys to make the whole system work. For local models, we're not there yet, but it should be easily doable thanks to the fact, again, we use light LLM to interact with the language models. Another key aspect we focused on was local deployment. So Buttercup was originally designed to run on several big Azure virtual machines. For the competition, we deployed something like 70 virtual machines with almost 200 gigs of RAM and 16 CPUs. But yet again, we had a lot of money on Azure credits to spend for the competition, and that doesn't work for people who want to use the system on one project, for example. So since we use Kubernetes to deploy the whole system, we rely on Minikube to easily deploy it locally. And with one command, you can easily do it. Let's say deploying it on a production-ready cluster in Azure is still just one command away. With Kubernetes, you can adjust replicas as needed. Another big usability factor is that you can now run the whole CRS on macOS and ARM, although it was the competition was originally designed for x86, and there were a few blockers to actually enable ARM support, but we did this extra work, and now you can run the system on your MacBook without needing any virtual machine or Docker setup to try it. And we also worked a lot on making the system easily runnable by everyone. So no complicated configuration files to deal with, no secrets or keys to regenerate, to make the various components communicate, tools to pre-install. We made sure to document things clearly, and we created easy-to-use scripts that allows you to deploy and run the whole system with just 2 commands, as you can see in this short video. So you do make setup local if you want a local deployment, or make setup Azure if you want Azure deployment to prepare a few configuration files interactively. And then with make deploy, you deploy and run the whole system. And even though it asks you for a few data and keys, you actually need just one LLM API keys to run everything, at least to start with. Last, we added support for C++ for now, which is very similar to C, of course, but it required decoupling us from what was originally designed for AICC. So we had to change our program model component to parse, for example, classes, fields, and methods, and other constructs that are not present in C, deal with the mangling and demangling name. But this is actually just the beginning, as we really want to see this working on new languages like Golang, Rust, Python, and so on. And there's still a lot that can be done on Buttercup, so we are just scratching the surface. And it's really important to make security tools easily accessible and usable to people. So it was part of our journey. There is Kubernetes auto-scaling that can be implemented, extra languages that say more agentic behaviors throughout the system, and so on. So with this long journey, we learned a few things. First, that LLMs are incredibly good at finding vulnerabilities and patching them. And we were a bit skeptical about this task at the beginning, especially for finding vulnerabilities. But with time, we actually changed our mind. We also learned to give LLM well-defined problems, so that by splitting problems properly, you could test components more easily and also achieve better results. And we also try to validate LLM outputs in a deterministic way as much as possible. Even though we did not have a deterministic way to generate the output, we could find some deterministic way to actually validate the output and allow the LLM to iterate on that. So with that, I'm done, and I'll be happy to answer any questions you have.
Cool.
Thank you.
Thank you so much, Ricardo, for the great call. And also thank you, Dan, for the opening remark. We have question for maybe one or two. We have time for maybe one or two questions. Let me start with the most important question from audience, one of the most important one. How can community participate in the development of Buttercup from now on? I saw you have done a lot of effort after AICC, but how to bring in the whole community to help with the effort?
Yeah, the project, as we said, is open source. We accept pull requests. There are a few issues that we opened since starting the repository with ideas we would like to work on. So that's a starting point. A few key points I've highlighted in the talk are also some starting point that we would like to see. So we are very open and willing to accept contributions from anywhere. And yeah, I said it's easy to start testing the system even locally and find things to fix. Also, by design, it would be very easy to integrate new components in the whole system and just integrate in the Minikube or Kubernetes setup. I'm not sure if, Dan, you want to add anything on this?
Hey, sorry, I'm double booked, so I had to join a separate meeting. I think the general question was just around community contributions and engagement with Buttercup. Yeah, we have a team of people that are dedicated to continuing to work on it. So we added some basic code quality and testing improvements since the end of the competition. So we are ready to work with people, and a lot of our clients are paying us to build custom additions and enhancements to the code base. Like we invested in building something that was flexible, that had an architecture that was maintainable, that was extendable, and the current system is reaping the benefits of those early decisions. So yeah, please work with us.
Cool. Thank you so much. Maybe another quick technical question. Well, we know that patching is for security, but how did your system ensure all the functionality also preserve when we deploy the generative patches?
Yeah, so I didn't talk about this, but it was in the diagram. But one of the first phase of our patching system was trying to build and run unit tests or tests that were available in the project. So after that initial phase where we could be sure that from the original project we could run tests. Then we tested again at the end of the process after we applied the patch, if we could still run all the unit tests or tests that were available.
Okay, cool. Thank you so much, Ricardo and Dan, for
Thank
your
you.
time. Yeah. Next, we will have Tyler from the theory team. They end up with the third place in AICC. Very, I personally like their system because it's very AI driven and the code is very clean. Without further ado, Tyler, the floor is yours. Thank you so much for joining us.
All right, thank you. I'm going to assume that everything's good audio and visual wise.
Yeah.
All right, cool. So yes, I'm Tyler from Team Theory. So I'll talk about kind of how our system's set up. I think a lot of people already talked about the basics of...
Sorry, Tyler, just make sure, are you sharing the right?
Oops.
Yeah, it's not full screen for us.
Only. All right. I thought it was good. Sorry about that. Let's figure this out. Give me a second. Zoom. How are we doing?
Yeah, now it's good. Thank you.
Sorry, thank you. Great. So I think most people already talked about kind of AIXCC in general, so we get kind of the overview. So I want to talk more about kind of the dream that our team has, right? And I think most vulnerability researchers or security researchers share, right? You have code, you put it into a magical box, and then all the bugs come out, right? And like big code, not just like any code. And so the problem is like, how do we make this magical box in a way that actually works? And this has been kind of the problem for decades, right? We have all of these techniques that people have developed for this, and they all work, right? Like people find bugs every day with fuzzing. They find it every day with abstract interpretation or even grep. But all of these have really shortcomings, right? So some of these are the obvious things, right? We have false positives, sure, false negatives. But there's also kind of these weirder things, right? Like all these techniques require that we are able to build our code, or at least we have all the dependencies. And this doesn't seem like a fundamental limitation until you start dealing with a lot of real world projects, right? You start, things have kind of ridiculous build systems, or maybe you have third-party vendors who don't want to share their code or who are responsible for integrating things. So this actually matters, right? We have big code, right? It turns out that a lot of the techniques that we have maybe start diminishing as soon as our program size starts increasing, right? It works fine on a toy example. When you get to 1 million lines of code, things start falling apart. We also have to deal with modeling, right? So if we're doing something like abstract interpretation or symbolic execution, we can't just say like, here's the code, figure out what it does. We need to lift this into some analysis domain, right? We need to worry about SMT solvers or something like that. And this requires that we have some sort of effort, engineering effort to do this translation, right? This is actually a lot of work. And this is why a lot of these things are very difficult to scale to new languages and so on. And the last thing, which seems really silly, but all these techniques require some really complicated or formal description of what it means to find a bug, right? It could be a simple description, right? Maybe a segmentation fault, some memory access violation is a bug. Very simple description, but that's missing a lot of things in the real world, right? We care about logic bugs. If you're dealing with cyber physical systems, the bugs that we have are much more complicated, right? We don't just care about crashes. We care about things like, did my insulin pump too much insulin, right? And if we want to have an automated system that can find bugs like that, we need to have a formal description so that the code can have some reasonable understanding of what this means. And so the thing is, when we look at how humans do this, it's a little bit different, right? Obviously, this whole graph is a little bit fuzzy with what's red and what's green. Humans have issues too. But if we look at kind of what humans do when they analyze code, it's very strange, right? I don't need to build code in order to read it and understand what it does. I can kind of emulate it in my head. If I really want to, I can probably find some tools that I can use to run small slices. I can find bugs that are in deep code, and I can work backwards in order to figure out how to trigger it, right? I'm not limited to shallow code. I can make a lot of assumptions. I don't need formal reasoning to understand that a cookie is tainted, right? I don't need to understand all of the system calls, all of the inter-process communication, and all of the whatever data flow to understand how a cookie got into something, because I understand what an HTTP request is. And humans have reasonable threat models. Humans have reasonable threat models that we've based on kind of real world data, right? I know what insulin pumps are vaguely. So I know that it's bad if they're misbehaving. I know that if I have a self-driving car and it's not stopping, or if the headlights turn off or something, that could be dangerous. And I don't need a formal description to do that. And so this magical box that we have, we'd love it to have the same properties, and it seems like LLMs ought to be able to work in a similar way. So what do we kind of want from this whole system, right? We want it to be cost effective, right? We have humans today, and humans can do security audits, but we need something that's quite a bit cheaper, or else this was a kind of fruitless endeavor. We need to be able to find real bugs. We need to have low false positives. If we're just giving a bunch of junk, then it's going to make people very upset. And at least for the context of AIXCC, we also need to produce triggering inputs and patches. So how do we actually build something like this, right? The obvious thing, right? I'm going to take the Linux source code and I'm going to drag and drop it into ChatGPT and ask it to find bugs. Obviously, this isn't going to work. So fundamentally, it seems like there's nothing really stopping LLMs, right? LLMs have some vague sort of human reasoning ability. That's kind of the whole hope. But practically, we have a lot of issues, right? The first is the obvious one of limited context windows. As we heard about in the first talk, right? Even though some of the context windows may be large, right? They may be labeled as something like 2 million tokens. We have a lot of issues even when we start getting anywhere near that amount. And when we're dealing with large code bases, even 2 million tokens isn't enough to fit the entire code base into the context. We also have hallucinations, right? If we just give our code base to an LLM and ask it for bugs, we're going to get a lot of random junk and false positives out. We have biases and things like that. So the basic takeaway here is like we can't just magically solve this using LLMs in one shot. But of course, we're not limited to doing this in one shot. So if we kind of think about how humans are solving this problem, humans don't read a bunch of code a single time with a single pass and then output a bunch of bugs. Humans come up with ideas. Maybe they read the code and they sleep on it. They come up with hypotheses and they test them. And so our hope is that we can encode kind of a similar workflow that we use as expert security researchers, and we can encode this into some sort of pipeline or workflow using LLMs. So the first step that we have in our system is basically querying the LLM against every function that we can find. And we give it some sort of pre-built list of bug types that it should be considering. And we output a bunch of data. We prompt it for outputting things about, did you find that bug? But not just that. We say like, are there sources and sinks that are relevant to this bug, right? It's kind of like forcing a certain chain of thought for each bug type to get it to think a little bit more. And the goal here isn't necessarily to solve things in one shot. It's to come up with as many good ideas for bugs as possible. So if we can come up with kind of all of the plausible bugs that exist, we can worry about false positives later. So we can just take a kind of a quick example of what this might look like. The actual prompt is very long. You can see it in our source code. I'll have a link at the end. But whatever, we're going to examine some code. Let's think about sinks for different categories of things, right? So we have some snippet of code here. And the first thing that you realize is this is kind of hard, right? I don't have enough context to do a good job understanding what's going on here. However, there's a few things that I can see right away with intuition, right? This is probably going to do a memory write onto the dest variable, right? I see a source in dest, I can intuit right away what's going on there. So we have something like a memory sink. We also know that cookie is probably attacker controlled, right? Again, I don't need to trace the whole taint through the program to understand what a cookie is. I know that a cookies come from some reasonable attack surface. And so maybe the LLM is going to output something like, great, this looks something like destination might be overflowing in this call. Is that correct or not? Well, obviously, it's very difficult to tell from this limited context. And so we still have kind of the same problem as normal static analysis of a bunch of false positives, right? So our false positive rate is incredibly high at this stage. But we have solved a couple of those problems that we set out to solve. So our bug classes are a lot more flexible here. We're not limited to saying it has to be a memory safety violation. We can say stuff about logic bugs or cryptographic bugs, and the LLM can make its best guess at trying to come up with hypotheses about what constitutes a bug there. The code doesn't actually need to work for any of this, right? I can give it anything that it can read, and it can read through it and try to do a reasonable job. So we have solved some of those big questions that we were trying to. And of course, if we have traditional static analysis, that fits into the same paradigm where it's, bug hypotheses, so we can fit that in the same workflow. So now our problem has shifted, right, from finding bugs to filtering bugs, right? So if we can find a way to remove false positives from a list of hypothetical bugs, then this approach can work really well. So the problem is, how do we do that? And once again, we don't have to do this in a single shot, right? Our goal isn't to take all of these things and instantly accept or reject them. So we can do this iteratively. So just as an example, these are kind of ballpark numbers to make some of the math nice and round, but they're approximately correct. So maybe we run on some code base and we get 10,000 reports, but there's only 10 real exploitable bugs, right? That's a ridiculous false positive rate. But we have a number of different tools. We have classifiers, right? We can ask an LLM to classify each bug as likely false positive or not. This is very cheap because it's a single shot LLM completion, but it's obviously not going to be very accurate, right? So maybe what we do is we set a rejection threshold that gives a 99% false positive rate. So we'll still get 10% of the, maybe take the 10% results. We can run agent triage. Agents are great. They're a little bit more expensive, so we can't necessarily afford to run that on everything. We could also run a full POV generation, which we'll talk about in a second, but that's relatively expensive and takes a long time. But there's not going to be any false positives because if we generate a POV, obviously it's a real bug. So again, rather than doing this in one shot, we can kind of do this iteratively, right? We start by filtering it down with the classifier, then run the simple agent, and then run the POV prediction. And this lets us do something like spend on the order of $1,000 instead of $100,000 if we tried to exploit every single hypothesis that we came up with. So how do we actually do this POV production, right? This is actually a huge problem because the approach that we decided to set out for, we're not doing this fuzzing and symbolic execution stuff necessarily, which would generate these inputs for free, right? The nice thing about fuzzing is if it finds a bug, you have a triggering input automatically. But we didn't do that. So how are we going to trigger these high confidence bugs? So some of the other talks discussed some similar ideas. So the first thing is you don't phrase POV production as an input generation in the sense of generating a string. It's generating a program to generate a string, right? So this is a coding task. There's a lot of nice reasons to phrase things like this. Part of it is that obviously LLMs can't really generate binary output because of how they're tokenized, so that's a huge problem. But they're great at coding, right? That's kind of, Python is kind of like the native language of LLMs. And they have lots of in-distribution training data, right? They've been trained on the internet. The internet has all sorts of POCs for triggering bugs. So this is a really nice way of dealing with that. The next problem that we're going to deal with is that we have to encode our inputs for a fuzzing harness, right? If we're given a program, how are we going to talk to it? And this seems a little bit silly, but when you're asking your LLM to generate code, if your target is something like a web server, it might try to be too smart and just send HTTP requests, right? It may not realize that its goal is to generate binary data. So just as a quick example here, this is a harness from the curl project. And if you look at this, so it's using the libfuzzer format, it kind of takes some opaque data stream and does some type length value thing with it. It's pretty difficult to understand what's going on. So what we do is we feed this to an agent. The agent has the ability not just to read the harness, but to read the surrounding code and come up with a Python kind of library function that can encode the input. So the nice thing here is it can come up with a semantically meaningful input, right? This takes 4 different strings, a URL, a user, a password, and a response, and it deals with all of the actual encoding. It can come up with some docs as well and feed that to the LLM. So the nice thing here is we don't need knowledge of vulnerabilities to build this encoder, right? This can run independently beforehand, and we can test it, right? We can test this independently by making sure that each of those data fields get to where they're supposed to be by using a debugger and saying, if it takes a username and password, did the username and password end up in memory in the variables that I expect them to? The next thing that we're going to run into is just that generating exploits or POVs for things is a really complicated problem. And the amount of data that we have to sift through kind of in this journey to do this is very large. And so we really want to be able to use something to compress our context or kind of keep it clean. So we use subagents as much as possible. So in that previous example, right, we can use subagents to determine this harness input encoder, and we get a relatively short Python snippet output. And overall, our POV producer, the kind of main agent that drives this process, has no code access, no direct code access. And this is very intentional, right? So code is incredibly long and distracting, right? If we see to-dos in code, obviously that's not exactly malicious prompt injection, but like these sorts of things can be really distracting, and our model has to decide what to attend to. And if we have thousands of lines of code, it's still going to provide some issues. So instead, we can answer questions about code with a dedicated subagent that is able to read the code and produce a short output. So the kind of architecture is something like this. So we have our POV agent. These other blue boxes are like subagents for these complex queries. So we see the nice thing is these subagents have the ability to read code, right? So they have some source reading functions, but these source reading functions are all very grounded. So they can use static analysis and traditional kind of code browsing techniques to do these things deterministically in a very reliable way. If they need to read a definition, they can give the symbol name or something, and we'll do all the work that we can on the back end. We can use grep, we can use gtags, we can use tree sitter or whatever we want to find where that definition is, and then feed it back to the LLM. So that part can run deterministically, and then the overall agent can do a good job. So in addition to those static source questions, we have debugging questions, right? So if it has some sort of script that it's generated that it thinks is a plausible POV, it can run that and debug it. It has access to a debugger and so on inside of that subagent. And then finally, we actually have to test the POV. Obviously, the agent can run this on demand if we want. But we also run it deterministically, right? If this POV ever succeeds, we can terminate instantly. And if the POV agent ever decides that it thinks that it has succeeded, we can run this test POV and make sure that it didn't lie and hallucinate. So, the agents are really nice. I think everyone who is here in attendance understands that agents are wonderful, but I do want to drive a couple points home. So obviously, agents are a lot more expensive, right? Your context length is going to grow quadratically because you have to keep going back and forth, repeating all of the previous messages that you had. So your costs run up over time quite significantly. But the context that you're able to get makes hallucinations and reliability much better, right? So it's a very powerful technique. But developing a lot of the tools around this, I think, is still a very nascent thing that we don't have good answers for. So the tools need to be simple. You need to include all the tools. But we've done a lot of research in like human usability studies and ergonomics, and we don't have a lot of the same things for LLMs. I think one of the big things about this in particular is that you really should not include extra tools. People think that tools are kind of like some option that you present, but if you think about it, these are specifically added to the prompt. And if you think about how this works, like I like to think about it kind of like a video game. Like if you're playing a video game and someone gives you a portal gun, you know what to do with a portal gun, right? You shoot portals at things and you jump through them. And if you're playing this game and someone gives you little jumpy stilt things, you understand that this means that you can jump to high places and you can fall from heights and you're going to be okay. So these tools, in a sense, are guiding how you're going to solve the problem. And if someone gives you lockpicks and you're playing the game of Portal, it's actually going to really confuse you, right? You're going to, every time you get stuck on a puzzle, you're going to say, wait, is this where I'm supposed to use lockpicks? You're going to go try and do these things, and it's going to get really confused. So you need to be really careful with that. So, that's all kind of abstract, so we can talk about this real quickly. There's a lot of text on the screen. We're not going to go through it all. Basically, we can run some system message, give our agent some information about the project that it's going to run. We can give it information about the harnesses and a bug that we're trying to exploit. It has access to tools, right? It can run these sub-agents. It can ask for more details about the bug it's trying to exploit. It can use a sub-agent to figure out which harness it's going to pick. Again, this is a nice example of compression where this is a relatively complex query. The amount of context required and source that it would need to read to figure out the answer to this question is quite large, but the overall answer is going to be quite short. Eventually, it starts generating some POV code, runs it through some debugger. The debugger is going to answer a natural language, telling it about kind of what's going on, blah, blah, blah. We get the idea. So this can run for a while. That example ran for about 40 minutes, and we can see the output. So it's able to crash the specific assigned integer overflow vulnerability that it was prompted with at the beginning. And the input for this is actually pretty non-trivial. So this is the full input, including the comments that the LLM generated for the POV. And here's kind of a hex encoding of it. So this is a pretty interesting vulnerability, especially because this is actually a 0-day in FreeRDP. So this wasn't something that was injected and meant to be found. This was kind of a real vulnerability, not found by fuzzing. FreeRDP is found, it's a OSS fuzz project. So there's a lot of things that this technique can do that kind of go beyond what's possible with fuzzing. So patching, I don't want to spend a lot of time on patching. I think there's a lot of interesting things here, but today people get the idea about what coding agents can do. I think this was a lot more exciting 2 years ago when we started, but at least, we get the idea. So overall, did we meet our goals? I think we did, right? This is relatively cost effective. Generating these POCs is something that we can do for a few dollars, which is kind of incredible. We can find real bugs, including 0 days. We found a lot of 0 days, exploitable 0 days in name brand software, let's say. Low false positive rate. We were able to produce triggering inputs and patches. In terms of us at Theory, we've done a lot of things post AXCC. So we have support for other languages, JavaScript, Python, Solidity. We can also run on binaries. So we can do kind of a similar technique running on assembly code. We have CI/CD integration. We actually run our CRS on our CRS commits now, which is kind of fun. So anyway, just to wrap up, I think LLMs can help work on this kind of human static analysis problem. You don't need to solve these tasks in one shot, right? Trying to figure out a workflow, separating kind of hypothesis generation and testing is a very general technique. We can design our agents to make things kind of more efficient and overcome a lot of these shortcomings. I also want to emphasize that this is one approach, and LLMs are kind of a really new and awesome technique that apply to a lot of different areas. So I think there's a lot of new ideas that still need to be explored. So our source code is also open source. I've got some kind of QR code here, got some blog post information, source code. If you want to browse those agent trajectories and read the whole thing, they're all there. But yeah, thank you.
Cool. Thank you so much, Taylor, for the great talk. Sorry, we are a little bit behind of time, so probably just directly start the panel session, and then we can ask you a question during the panel session as well. So it's the same. Yeah, maybe let's start. Tesu, Ricardo, and Dan. I will start with the first question since we are discussing AICC. I have seen a lot of new technology being developed during the competition through these 3 amazing CIs. For each of you, could you please maybe summarize a little bit the key strengths or innovation in your solution? Maybe you can start from Taylor since you just finished.
Sure. Yeah, I think for us, we have a we've done a lot of things around fuzzing and kind of these traditional techniques. It's not something that we are not familiar with, but I think that our whole hope, and hopefully what we've proven, is that it is possible to use LLMs to mimic this human workflow and do a lot of this stuff kind of directly in a way that there was really no tools for previously. So I think there's still a lot of work there, but I think that's a big innovation and a big exciting area.
Right. Just a quick follow-up before we go to other solutions. You mentioned like we want to LLM to like simulate a human workflow. I totally agree that should be like our end goal. And then you build all those sort of like agents with sub-agents. What's the kind of high-level like mindset do you have when you build the topology of these agents? Right? Like I remember having like hundreds of sub-agents working together parallel. So what's the principle there?
I think a lot of it is trying to think of basically how, again, if I was a human working on this, every time I'd kind of like do some sort of context switch or try to answer a question anything that's a simple question that has a simple response is probably something that could be an agent, right? And again, both for context compression purposes, because a simple response means we get to compress a bunch of context into a small answer. But also just for kind of this division of labor purposes that seems like a reasonable trade-off. I think there's a lot of questions still about like, you do want to share some information about memory, things like that. So it's not entirely clear, but yeah.
Okay, cool. Thank you so much, Taylor. Maybe Tae-Soo, you can answer the question as well.
So I really like many of the decisions that Theory made for the competition. And we also had tons of interesting research ideas that we wanted to execute, but because it's a competition, and we also wanted to win. So we actually made lots of practical decisions behind the scene. I think one of the most important criteria for us is how to maintain fault tolerance. I think, in fact, it turns out that's the most significant, most important aspect of the competition as well. Your system should function for, say, 4 to 5 days without any interruptions. You should be able to analyze random repository, and there are tons of surprising things happen during the competition. It turns out our system also suffered from many of the issues. We couldn't even build many of the projects. We skipped the entire project, for instance. But at the end, some component arrive during the competitions and start progressing. I think that's actually very important for the competition, probably very important for the real life as well. When we're designing some autonomous systems in the future by using AI, but I think more practical way, I really like how Theory organized everything, and also like what Buttercup design and semi automated way. This is what we actually did for internal deployment at Samsung as well. We also have web user interface. We don't need tight integration between bug finding and patching. And patching is not always correct. So we give you more chance for developer to iterate over their automatic generated patch before generating PR to the GitHub. I think these are interesting directions, but I really like the fault tolerance aspect of our CRS design for the competition.
Cool. Thank you so much, Tae-Soo. Anything you want to share, Ricardo?
Yeah, I think one of our key strengths was finding a good balance between traditional solutions and LLMs. We used LLMs where we thought they were good at, and traditional solutions for problems they were good at. So we leveraged the strengths of each world. And yeah, we focused first on a robust and stable system that could work reliably. So I think that paid off for us.
Cool. The next question we receive, since this is AICC, we talk about AI. From your experience, how much does each step of your CIS benefit from AI assistant? Which step you say the AI jump in and help the most? Which step you say AI is not playing that important role? Maybe we can still like go back to original order, start from Tae-Soo and then 12 bits and then Siri.
I think many of the CRS in the final design of our Atlantis heavily rely on AI, I would say LLM. Previously, most of the program analysis, it seems like, again, as Taylor mentioned, is great in terms of their idea, and in theory, they should work. But in reality, for one of the good examples is symbolic executions. We had a huge problem of just enabling symbolic executions in any of those open source projects. It's too big. And instrumentation and during the compilation process, it breaks something very unexpectedly in every single project. So how to deal with those? And LLM, as the theory mentions, like has a fundamental benefit of resilience because they just process the text-based reasoning, and then they can do some actions at the end. I think this is a remarkable benefit. So if you think about what are the things traditional software analysis you can replace with LLM, that's a very interesting idea. Your idea is widely open. One of the key idea, one of the interesting idea we discussed heavily in our team is how to replace concurrent executor with LLM. In fact, in theory, there's some places like checking the correctness of comparison by using hashing function. You never be able to proceed if you have a concurrent execution behind the scene. But LLM can recognize, hey, this is a hashing function. It's not core features of the program. Hey, just replace the hashing function with identity. In fact, this is amazing decisions. To oversimplify the input, not relevant to the original constraint to the input space. In fact, there's a potential that LLM can significantly improve the possibility of analyzing large real-world software outside.
Thank you. Ricardo, anything from, yeah.
Yeah, for us, I think for the patching side, AI, of course, has helped tremendously. Like before, there might have been tools to patch autonomously a subset of use after free or a single class of vulnerabilities, but now like the problem is much more easily solvable. For our vulnerability discovery step, instead of say, AI could improve a lot on that part for us. And yeah, applying approaches like what Thierry and Team Atlanta did, more agentic behaviors on the vulnerability discovery side. Instead, like for us, it was more of a using LLMs to help the fuzzer. We could rely more on like the LLMs to do the actual work. So, and like it could improve even more our system, I guess. So there's space to improve there.
I think yeah, like to Ricardo's point, patching, like I guess if you think about all this, Tae-Sik Kim mentioned the Cyber Grand Challenge, right? That was 10 years ago. And in some sense, all of these things like automatic bug finding is possible, right? We had that before LLMs. There were no GPUs in the Cyber Grand Challenge. But some of the things that changed, right, is being able to run on source code and like produce patches that humans can look at and be happy with. It's kind of incredible. And even the traditional, we have program synthesis techniques and things like that from academia, but those don't work anywhere near the same, and no one would like those as patches. So I think that was a huge thing that everyone immediately made use of. I think for us also the POV generation, right? Finding bugs you can still do with static analysis, traditional techniques, but the actual converting of this seems like it could be a bug into here's an input that triggers it. There's not really another alternative aside from fuzzing or something like that, but for targeting a specific bug, you basically need LLMs or something like it.
Okay, yeah, thank you so much. I feel that makes sense because LLM are generative models. So in terms of generating new code, like POA is also part of generative tasks. I'm good at it, which make perfect sense. Probably like talk other side of the story is that we know like during the process, we use LLM extensively, so do have experience also regarding the good and the bad. Let's talk about the bad side. Like from each of you, what do you say the key limitation of current LLM in terms of finishing all these tasks? Right, so maybe we start from here. Yeah, so what do you say the key limitation of LLM in your experience of
I
team
think
lifetime? Mhm.
one of the things that the
Mhm.
organizer or AICC in general didn't
Mhm.
highlight enough is that there's a huge chance that LLM already observed all the open source projects that we analyzed during the competition. I think this is weird, but you can think the amount of budget in the organizer side that they cannot create the ridiculous big project for the competitions, right? This is a little bit weird. But at the same time, because LLM already trained on top of those commits, so they're leveraging some of the recall or some of the memory residue inside the weights when generating patch and stuff, probably work out pretty well. But in terms of real world code repository, for example, some internal code bases is Samsung, and none of the LLM actually observed. I think we see some huge performance gap between, particularly when we are handling large source code repository. I think we need some form of online adaptations if there is a chance to do the very short fine tuning on the code bases so that we can respect some of the coding conventions inside. And similar to human learning about the code base, we need some, before doing anything, probably LLM should do some adaptations and generate some rags and index and whatnot, so that capture some of the big idea before doing any security task. I think there's a little bit of gap between what we demonstrate in AICC and when we are actually handling larger scale source code that they never saw before.
Yeah, exactly. Data contamination is one of the pain for us as well. Like sometimes you feed model with the function, the model automatically tells you what are related functions because the model has been trained on it. But yeah, as you mentioned, if this internal code base model cannot do this, and then there's not enough context, model may make mistake for sure. Yeah, so like Ricardo, what about like your experience? What's the key kind of pitfalls of LM?
Yeah, I agree with you, Kim, on the aspect of handling non-open source projects. Like this was also one of my faults because, yeah, would the AICC work that well if it was on big closed source projects? It would be nice to see. But yeah, that's an important aspect. And in terms of limitations, I think there is one aspect I would like to highlight, which is the indeterminism of LLM models. Because like you could try the same prompts, the same inputs several times, and maybe one time out of 10, it will give you the right answer. It will think about the code in a slightly different way that will unblock a whole different path. And this indeterminism is kind of, we could say a limitation, but it's also slightly different from other security tools we have because with other tools, you get like you have the same input, you get mostly the same output usually. But with LLMs, there is this indeterminism that make applying LLMs for security tools a bit harder. Like with agents and iteration loops and so on, you can reduce this, but yeah, it's still kind of a problem, or yeah, a slight limitation, I say.
Yeah, I think just kind of in a similar vein to what Ricardo is saying, there's evaluations of these systems is really obnoxious, right? So especially when you have an agentic system, one of the really cool things is that your agent might run a tool and the tool totally fails and the agent handles that robustly, right? It tries it again with different arguments or it switches tools to something else. But if you're trying to build this system, it's very obnoxious if you introduce a bug and the system just kind of, it's okay, I won't worry about the bug, I'm going to keep going. And it doesn't fail, but now it takes twice as much money to run or something like that. And so every time you want to do these evaluations, like if you have to run everything end to end, it's super expensive. It's just, I think that kind of as software engineers or researchers, we haven't really figured out how to really work with these tools in the most efficient ways. And I think that's kind of the main limitation in my mind.
Interesting. So we talk about randomness, talk about like stability of the two AI themselves, talk about data combination. But what do you say the limitation of the capability? For example, is there any limitation we have seen for like certain type of bugs, the model just cannot analyze it? Right, from like capability perspective, what do you see the limitation?
I don't know who that's directed at, I guess, since I went most recently.
Yeah, maybe you can just.
So I think, there's some things where there's definitely a lot of biases in how the models are trained, right? So even like when we switch from one provider to another, we'll see things like maybe they're very safety tuned and they really hate saying that, oh no, that's a false positive, because false positive means that you're making a very strong assertion that something is safe. So there's a lot of these biases around kind of that sort of thing that I think are quite difficult. But I think fundamentally my belief is that, if we stop doing like LLM like frontier models today, I think there's still a lot of like probably at least 2 years of research that could keep coming out of using the exact same models with the capabilities we have today. It's like I really think that obviously there are limitations, but the limitations are really on how we interact with the models, and it's better models are better, but I think it's kind of a human tool interaction problem as opposed to a model problem.
Sure. Anything you want to share, Tesu or Ricardo?
So when we are writing software in general, after several interactions with the software and their design, we can think of next step. Hey, this is a way to improve, and this is the work that we have to for the next round of iteration of our systems. When we are writing agent, we realize even after we're completing this, we don't know what to do. Tinkering around the prompt, tinkering around some of the architecture, hope that it work out. This is a little bit annoying as a program. And then my workflow these days is that I'm really particular about certain implementations. Now, instead of solving it, I try to ask agents all the time, which feel like I'm dumb anymore. and at the end, I start analyzing their output and try to comprehend their logic behind, which is almost impossible. And this is a similar problem in improving model capability. Probably after they train on certain data, other than increasing the amount of data, like what are the next, if you truly understand the model architecture, you should be able to say that this is a way to improve, right? But we don't know what's the next thing to do. In fact, no one in the world can propose other than keep trying and hope that it work out. In fact, this actually reflects how we did in our development, in our agent side. We don't know what's the best model. Hey, try to just put all the complex tools. Hey, it seems like it's directed too much. Hey, let's just simplify the tools. Hey, we talk too much in the prompt. When you're using reasoning model, don't say anything. Like all these random brute forcing in human developer side is super annoying, and probably the fundamental, like it actually took out most of the joy of development when we are building some of the agent for CRS in our team.
Okay, thank you, Tesu. Ricardo, what do you think?
Yeah, I agree with them. But also, I think one of the main limitations is what you have, I think, in the training set, like working on some topics that were not well covered in the training set can make, of course, the LLM work harder. But also it depends on how you interact with them, as Tyler said. Like maybe you can work around some of those problems they have with some specific language, or maybe working with binary data that seems to be harder for the models to reason about. Maybe you can transform the original problem you have into something that the LLM can understand. Like as we say, most of us has generated Python code to generate the input. We didn't ask the LLM to generate the input, and that's kind of one of the limitations. But we worked around that with some extra tooling. So I think there are of course limitations, some languages or topics that LLMs might not cover well, but we can find ways probably to deal with them.
So I have
Go.
another point that I like to highlight is that
Mhm.
the feeling that I have when you're dealing with this LLM, my software is not future-proof, meaning that we believe there's a new capable model, like say GPT-5, which actually appear immediately after the competitions. Most of the software actually adopt to the latest model, like latest improvement in the other side. But what we experience is the opposite. Although it improves certain area, but there are larger pros and cons, and certain workflows work better and the other work not. And the software that we're building probably become obsolete if, say, AGI exists in the future, or drastically improve prompt. Why do we need agents? We just solve everything, right? So many of the things that we are working on right now is all about how to address incapability of existing LLM. And by creating some structure in a way we can tackle very small problems that we really care. But said that, today's LLM is capable enough that we can utilize them in right way and useful way that we never thought of possible. But most of the work that we're doing will be very quickly obsolete if we have much capable model in the future.
Yeah, this is exactly the good point. We have seen during our competition experience as well, model gets updated and a lot of things we build is longer useful.
Yeah.
Since we talk about this, we have like two other philosophy level questions we want to ask before ending this panel discussion. First is that what do you think AI will beat human or surpass human capability in terms of cybersecurity tasks? Do you think that is possible? If yes, do you have kind of like inversion of the possible timeline?
If you're asking me, probably
This is funny.
surpass is a little bit overall the term. For example, in speed. In fact, one of the I don't recall one of the team actually participated in the live CTF in the final last time. Before human understanding anything, the agent actually discovered the flag and got the flag and submitted the score. So in terms of speed, for low-hanging fruit, LLM actually does pretty good job. But convoluted task or some complex tasks, human might be faster in terms of end-to-end manner. But one of the things that we can apply those LLM-based techniques, anything they can horizontally scale. For example, given a lot of number of embedded devices and websites, applying those agents in horizontal scale, you can easily beat. And this is not a future AI. The current AI already beat human in the scale because we have limited time and limited resources. But if you talk about the complex, say, can you find the zero-day vulnerability? Can you do better than most capable human outside? Probably still take time, but the people who have access to those LLM might be able to leverage even quicker and much better than AI alone, for sure.
Mhm. Yeah, Ricardo, what do you think?
Yeah, I think AI has kind of become already in some aspects a sort of replacement for human. We have seen it like with the Expo. They can do some, they can find some very nice vulnerabilities in some specific topics, but in the general sense, I'd say it's more of a tool, and I hope it will remain a sort of a tool for experts to use. So of course they will make us faster, and maybe we will shift like our focus on some more novel tasks and leave these easier tasks to an automation tool, AI or not. But yeah, I hope in the future we will just shift focus to more novel and complicated tasks more and more, and it's just gonna remain a tool.
Cool.
Yeah, I mean, I think I have kind of the same opinion, right? It's like if you asked, when are fuzzers going to surpass humans? Like in terms of total number of bugs found, I imagine fuzzers have long surpassed how many bugs humans have written or vulnerabilities, POCs people have written. But that's not how it works, right? Like a human uses the fuzzer as a tool. We have like this for a long time when people were talking about kind of AI, kind of the last time people were talking about AI, we had kind of all this discussion about like centaur chess, right? You have these automated chess engines, but you pair them with a human, and it turns out, at least for kind of like 2 decades, that was still beating state-of-the-art chess engines. Now I think it's no longer the case, where the human's just not useful. So I don't know how long it's going to take before, the human has no place. I think there's still a lot of very novel things that humans come up with, right? Like CPU level attacks, or like kind of weird logic bugs that I think are very difficult for computers to reason about. So I think that sort of thing is going to remain in our domain for probably several years. But Stacey Kim said, like, there's totally places today where obviously these systems are faster, they can scale better. So in some sense, they're beating certain aspects of humans already.
So I think I also have some anecdotal examples. We discussed those subjects a lot in our lab with our PhD student. After participating in AICC, as a hacker, we've been exposed to AI, and they realized, hey, that we can be replaced. So instead of being replaced in the future, hey, let's be part of the other side. So let's replace together. That's why they're creating PhD program. All of them now start a company because they don't want to be replaced. So they are the capable hackers and programmers, and they felt threatened in some sense. So it's a good time to be in the other side, finding a way to replace the human hackers, at least expand the capability of auditing to the older people, which previously only limited to the resource-heavy company, for example.
Cool. Thank you so much. We have one last question, but since we go over time a little bit, let's try to keep the answer short. But we do want to get your opinion on that. It's very important. It's follow-up of the current question, like who do you think will benefit more from AI at this stage? Attacker or defender, either in the short term and in the long term? Yeah, maybe
So
you can say.
if I start, I think Defender has more capability of utilizing their hidden proprietary information than Attacker. So I think I like to see more efforts like XBAL in more white box testings in the developer side, rather than pure black box testings in offensive side. Because Defender, as a developer of the software, they can decide how much information they can share together with LLM. I think short term and longer term is always have better capability in terms of protecting one single software, targeted software that you care about security. Because attacker side, again, similar to horizontal scale, you can tackle one of the components. But I think as a defender side, it's a good tool to leverage before exposing most important asset, your source code, to the attacker side.
Gotcha. Thank you so much.
I actually think that in the short term, attackers might have an edge, as AI is just yet another tool in their arsenal that they can use to find one single hole in a system, and they need actually just that. So they don't need to secure a whole project. They just need to find one vulnerability, one crash, and they're good to go. But in the longer term, I think defenders will actually benefit more from AI as they integrate AI more in the development, CI/CD. Think about like applying Buttercup or similar CRS in production during development. So it's gonna become more integrated with the development, and it's gonna benefit the defenders, I think.
I think I'm on the optimistic side. So I think right now, attackers already have the capability of developing exploits. Like, that's not a novel capability for them, although maybe their efficiency increases. But I think the defenders right now have very limited ability to find these vulnerabilities, maybe because that's not their skill set, or maybe because they're busy with other things like patching. So I think adding the capability of vulnerability discovery to defenders, I think that's going to benefit them significantly. So I think that this is a defense favoring capability overall.
Hey, thank you so much, everyone. Thank you, Taesu, Ricardo, Dan, and Taylor for the great talk and for the great panel discussion. We learned a lot from this session. Thank you so much again, and congratulations for your great achievement in ICC competition. It's super amazing.
Thank you so much for having us.
Thank you.
Yeah, thank
Thank you
you.
for having
Thank
us.
you.
Thank you. So from now on, we will start with session 2. The session 2 will consist of 3 talks from Frontier AI Labs, the OpenAI and Anthropic and Meta. And our first speaker is Newton Chang, and he's the cyber lead in the Frontier Labs team at Anthropic. And Newton, please take it away.
All right, thank you so much. Let me go ahead and share my presentation really quick. Here we go. Hi, everybody. Like Eugen mentioned, my name is Newton Cheng. I currently lead the cyber portfolio of a very interesting team here at Anthropic called the Frontier Red Team. My talk is, the goal of my talk today is to just talk a little bit about kind of how we at Anthropic are sort of viewing the really the problem of cyber offense being accelerated by AI, increasingly powerful AI models, and kind of what we think we should be doing about it. So just as a little bit of an introduction to what my team does overall, we are called the Frontier Red Team because in some sense what we're trying to do is we are trying to figure out what the worst case scenario for cyber misuse of increasingly powerful models looks like. We do this by trying to measure capabilities based on our experiments. We try to predict when models will have certain levels of capabilities. And what we ultimately hope to do is we hope to demonstrate these capabilities that we are saying we should be concerned about in a safe and controlled setting. And what my team does is we specifically consider the concerns around cyber misuse. And so some other words that some folks in the audience might associate with this type of work is dangerous capabilities and risk, kind of everything under this umbrella. I don't usually like to stick to these phrases too much because I think they're just really broad, and I'd like to be a little more specific about what we actually mean by this. Now, traditionally, what we've done is we've tried to talk about threat models, and this is a slide taken from a talk I did at DEF CON CTF and the AIXCC hub earlier, or so not DEF CON CTF, at the DEF CON conference earlier this year, and the question always comes back to like threat models and trying to be like really specific about, oh, here is like the risk profile that we're concerned about. Here are the threat actors we're concerned about. Here are the types of capabilities that matter. I think many people, both on this call and in the audience, probably already have a pretty decent idea. So I don't plan to go really in depth here. What I will mention is, I think, at a very high level, we sort of think about 3 types of actors when we're thinking about cyber misuse. We think about, on the left here, we think about, AI as a tool that can upskill relatively low-skilled actors into looking like higher skill actors. We think about threat models that look like, at least in terms of impact, significantly increasing the scale of relatively low-level attacks. For example, you could imagine like massively increasing the scale of relatively simple ransomware or phishing type attacks, things that from a technical perspective maybe aren't so impressive, but AI kind of enables someone to do this at much larger scale. And then there's a threat model, I think, that is more unique to AI models. The first 2 threat models, I think, are sort of very commonly attributed to even standard every pen testing tool that's ever come out in the security space. And I think something that is in some sense quite unique to increasingly powerful AI models is a threat model that looks like elite actors able to become significantly more efficient and productive through the use of AI models, such that they can essentially parallelize or scale out their workflows, so that instead of just one APT group or one actor performing a single operation, they're able to parallelize and increase their workflows to like 4, 5, 6, 7 APT level or elite operations. And again, I won't go into too much detail about like the specifics of these, but at a high level, these are kind of like the 3 types of risk actors that we're thinking about. Now, I think a traditional story for the way that the community and we thought about this problem even just a year ago was we thought, okay, you know, what we need to do is we need to get better evals in place. We need to make sure that, you know, we have all these things like methodology and mapping evals to types of capabilities kind of on point. And to be clear, this is still really, really important. I think, however, that one of the changes that as a frontier lab we've gone through in the last 12 months is we've kind of moved on in terms of how we think about and how we're using evals internally. Certainly, they're still useful for things like tracking capability progression, but we've sort of progressed internally, at least, into treating evals almost as just milestones for capabilities that we expect to reach. I have here like a Slack post from one of my team members from our recent 4.5 release, where kind of in some sense the absolute value of evaluations is somewhat less important to us than just like models being able to do things that we thought they couldn't do before. And the way that I've been phrasing this in the last few months has been, I think, our thinking around evaluations, at least within our lab, is that we are trying to move as much as we can from models doing proxy tasks that we think map to capabilities that we care about to just trying to get models to do the actual real thing that we care about when we talk about, model risks or risks of cyber misuse. And so, for example, one of the kind of classic scenarios that we think about in terms of cyber misuse is, people will try to use AI models to attack enterprise networks, or they'll try to compromise networks of industries that are important to the economy, to the infrastructure. And to that I say, great, rather than us trying to piece together proxy tasks of evaluations, sort of some types of capture the flag, competition, capture the flag challenges, something that map to very specific parts of what that process might look like. My team is very much in favor of, okay, well, we should just try to build as close as possible a facsimile of what compromising one of these networks looks like, and then throw our model at it and see what happens. See if it can do it. If it can't do it, where is it failing? And for an example of what this actually looks like in the real world, I've put this link here of our wonderful safeguards team who have been working like crazy for the last year. A couple months ago, they released this really great threat intel report where they put out some of the most interesting case studies from the last several months about actual real-world usage of adversaries trying to leverage our models to do cyber misuse. And there's some really, really nice examples here, including, for example, a probable Chinese APT trying to compromise Vietnamese infrastructure and telecommunications. There is a nice story of how we disrupted a North Korean fraudulent remote employment operation that was trying to leverage our models for that, which is all just to say, following up from the previous series of talks, we're already pretty deeply in the regime of people in the real world, of adversaries in the real world, already leveraging our models to try to undertake real cyber operations. And I think that, especially within the frontier labs, we're not really in a position where we have the luxury of just looking at these types of proxy tasks that aren't necessarily fully representative of what is actually going on in the world right now. We tried to do this sort of earlier this year in a collaboration we had with Carnegie Mellon, where we demonstrated that Claude back then, I think that was that was Sonnet 3 to 3.5. We demonstrated that it was able to replicate the Equifax operation from several years ago. And that, I think, really kind of started our push internally, or certainly my team's push, to say, okay, it was able to replicate things that were able to happen in the past, and now combined with the types of real world examples we're starting to see in these threat intelligence reports, okay, like we are firmly past the point where models probably can't do things that are actually useful for even, I think, APT level actors out in the real world. And I think ultimately the most concerning thing about where this leaves the state of cyber offense, this leaves the state of cyber offense augmented by AI, is you could imagine a world where you have a model that is not just replicating Equifax once, but is, you can spin up like your 100 different agents as long as you can, pay for the API costs, and you could be running like 100 Equifax operations all at the same time, and for relatively cheap. And so this is sort of like the state that we find ourselves in the near future of, okay, this is what AI augmented cyber offense might look like. And so going back to my slide about, okay, here are these like 3 threat models we're thinking about, I think the picture that you want to have in mind is, okay, this isn't just a case of, like a standard in the same way that maybe a traditional pen testing or red team tool might have, where it sort of makes a particular or single workflow easier to work with. We want to be envisioning a world where, okay, when we're talking about AI assisting adversaries, we're talking about AI models that are increasingly powerful, that are increasingly autonomous, that can, we think, like very soon reach the point of being able to do near autonomous end-to-end cyber operations. And that, I think, is like really the sort of concerning place that we need to be building to, or we need to have in mind as we're kind of figuring out what should we do about securing our own systems as well as possible. And so maybe, unsurprisingly, and based on the title of the talks following mine, I think that the conclusion that a lot of the frontier labs have come to certainly is, okay, well, the way we combat this is we need to be trying to leverage our AI models for cyber defense as much as possible. And so what my team is thinking about, what we as an organization at Anthropic are thinking about, is we're thinking about it first, I think, from the perspective of, all right, well, we know that models are able to, maybe with some assistance and increasingly less assistance in the future, start to do cyber operations. We know we have real world examples of elite level actors trying to deploy AI models to perform their operations. Okay, well, if we can use those same capabilities, we can use those to find gaps in our own security posture. We can use those to find the places that our systems are insufficiently defended against, and then significantly accelerate our workflows for actually securing those systems. I think this is like a philosophy that is probably pretty commonly held by most people in the audience from the security industry. This is, in some sense, the classic, yes, offensive security is a key and integral part of actual good security posture. I think really, in some sense, the only message I have from that perspective is, okay, well, you really have to mean it when you're trying to use these models to red team your own systems. You really are trying to emulate as much as possible what actual adversaries are doing. And for that, I mean, I think there's really a non-trivial amount of work that goes into taking a model and figuring out, okay, how can we elicit the maximum amount of capability from these models? In some sense, that's like the core mandate of my team under the Frontier Red Team. We try to maximally elicit models to figure out what they can do. But that's all just to say, I think that as we are doing evaluations, as you are running these types of simulations with the models, it's really important to try to give models as much as you can to make them as good as possible. And this means giving them the full suite of tools, for example, that actual security researchers or actual red team pen testers would actually be using. That it's not good enough to run evaluations that look like, here is just my base model that doesn't have any tools except maybe a basic like Bash or Python tool. You really got to give it like the full suite of things, because certainly the adversaries out there who are trying to use your models to do bad, they are not going to only give the model the minimum number of tools possible. So that, I think, is really like the first level of what a good cyber defense looks like and how we can leverage our models for cyber defense. I think the next level is to say, okay, well, suppose we have a good handle on the offensive security side of things, which, to be clear, we don't necessarily have. But what we should then try to do is we should also try to deploy our models or use our models to do active defense that looks like, hey, models, find vulnerabilities in our code so we never even ship like buggy code that is vulnerable. Hey, let's use our models to try to help secure the open source community and try to minimize the risk of, for example, like supply chain attacks on some of the most widely used open source software and packages on GitHub. Hey, let's do things like just do responsible disclosure of CVEs in these things so that we can mitigate or we can shrink the total surface that attackers have of actually deploying models for cyber offense. So I think a really key part of what it looks like for us to successfully employ AI models for defensive purposes is exactly, hey, let's use models to actually secure our code. Let's use models to secure our systems in an active way. And then the next level after that, which I saw my colleague Joshua Sachs might later be talking about from his perspective, is we can even go one level further and try to then deploy autonomous agents for cyber defense that are actively securing your systems, actively hardening your systems and code bases beyond just what you might be doing at the developer level. And I think ultimately, this is really the posture that we really need to get to, where we are using our models to massively accelerate and scale out both our offensive and defensive security posture, because this is essentially, in my opinion, the only way to meaningfully defend against the wave of AI-augmented cyber offense that, again, we're already seeing. And so it's not really a question in my mind of what should we be doing, but these are all things that we need to be doing. And I think if you only take away a couple messages from this talk, I would say, one, models are getting a lot better. For people who might have looked at the blog post we released alongside Sonnet 4.5, you might have seen we had these evaluation results about model capabilities. And I want to emphasize that it's not the absolute value of evaluation performance that we care about, but rather the main thing to take away from our results is, hey, the gap between the lowest, this gray line and the top level orange line is 7 months. And we're obviously only going to be going up from there. And so, the main takeaway, I think, from my presentation is models are getting increasingly powerful. People are already using this to try to do bad things and try to do cyber offense. We need to be right now building our systems with that expectation in mind. We need to be arming defenders as much as possible so that they have a chance at keeping up with the massive scale of AI cyber offense that we might expect to see in the very near future. And that's all I got. Thank you so much.
Thank you. Thank you for the great talk. So we can have some Q&A session, and we got like some questions from audience. And the audience said that the categorization of threat actors for threat modeling AI is interesting. Is it based upon some assumption or threat intelligence on IOC, TTP as of the threat actor?
Yeah, so this is definitely an ongoing discussion. I think that this certainly my description was pretty high level. it's partly informed by sort of historical ideas around threat modeling in the cyberspace before AI became a big thing. In some sense, a lot of AI tooling follows a similar path to other like red team or pen testing tools in the space. But certainly, I think, and especially in the last 18 months, increasingly informed by our internal threat intelligence efforts, by what our safeguards team is actually seeing people are using the models out in the wild. And like I said, I think we've already seen examples of essentially all three of these classes of actors, and we're continuing to improve our ability to catch and disrupt these operations.
Thank you so much. Because the time is up, and we will cover more questions in panel session. So yeah, see you again soon.
All right.
And
thank you so much.
Yeah, thank you so much. And the second speaker is Ian Berlinski, and he's the research program manager at OpenAI. And yeah, thank you, Ian. Yeah, please take it away.
Hello. Hello, everybody. Let me see whether I can get the slides up as well. Are they actually presenting? Can you see anything?
Yeah, I can see your slide.
Okay. All right. So I'm the research program manager for cybersecurity research and products here at OpenAI. And I'm going to echo some of the same themes that Newton brought up, but also from a different perspective as well. So the main topic that I'll be chatting about is how we advance AI's defensive cybersecurity capabilities and how the community writ large can get involved in getting that done and moving the ball forward with making AI better advantage defenders. And I'm going to get there by a kind of roundabout way, starting with talking about the Zoom tab isn't working. There we go. Starting with an announcement of our recent product from my team called Aardvark. Some of you might have heard of Aardvark. If you've been involved in AICC or you're part of any of the security blogs or Twitter threads, etc., you've probably seen news about OpenAI's Aardvark. Basically, at a very high level, what Aardvark is a code security agent that connects to your Git repo right now, builds a threat model of what your code does and all the surfaces, etc., and then scans it and finds vulnerabilities in those commits, validates those vulnerabilities in a sandbox, and issues patches through our product codex, and then pushes that forward for human review. I don't bring this up to convince people to necessarily sign up to beta test Aardvark, though it is open, but rather to highlight just how much models have advanced over the last couple of years. We started a few years ago with a lot of the AICC work, focusing on whether or not people could even do something like this, whether people could advantage defenders over attackers by leveraging AI. So there's been a lot of work across different dimensions like code security, network security, privacy, etc., in looking at how far we could move the ball forward with advantaging defensive uses of AI. And the goal of this obviously is that AI is a helpful agent that augments human beings and makes defenders' jobs easier while making attackers' jobs more difficult. There's obviously a balance to that we all recognize, and that Newton, you spoke to from Anthropic's perspective. But we definitely believe that AI will advantage both sets, attackers and defenders. And our goal is to make sure that we advantage defenders more. And so in order to do that, this is a community effort, and we need the help of everybody to move this forward. So starting a few years ago, DARPA had the AICC challenge, and I saw in the previous session there were some competitors from the AICC challenge there. And it really opened the door to autonomous agents that advantage defenders with code security. And I've been involved in this from only about a year and a half, 2 years ago when I started at OpenAI. But it's been incredible how far the technology has come just in that time. And you can boil it down on why the technology has advanced as much as it has. And you can say that it's because people have been spending more time on it. You can say that teams have built better systems or whatever. But underpinning all of that is that the models keep getting better. And you can offload more work to the models that previously you had to orchestrate around. So about a year and a half ago, and these are evaluations, by the way, for cybersecurity that were performed for our preparedness framework. About a year and a half ago, the best models we had were kind of getting some questions right in some high school level challenges. They weren't really doing that great in professional level things. And most of the models required a lot of hand-holding to get them to do what we wanted them to do. With the introduction of reasoning and tool use, the models have become so much more powerful at tackling harder and more complex problems. And it's not a linear scale of it does these things just simply better. It's that it's unlocking whole new skill categories within the model of how to tackle these problems, how to think about these problems, how to orchestrate across much more complex sets of data and get to the answer that we're looking for. And I think this line is going to continue going up. I don't know whether our current benchmarks are going to be able to capture the nature of this line, because we're already approaching, and this data is probably about 6 months old, but we're already approaching the limit to the benchmarks that we've got. And so that begs the question: how do we really push this tech forward and make it something that superpowers or supercharges the humans involved in defensive AI? And that brings up the question of what matters in training, what matters in evaluation of these models. And right now, some of the evals could definitely be better. So what worked probably about 6 months to a year, 2 years ago, isn't necessarily challenging for the models anymore. And so simple evals where we're getting a correct answer out aren't quite as powerful as evaluations that are more representative of the entire environment, have more complexity, have the skills that we need to elicit out of the model actually tagged and understood, and we have more clear understanding of what skills need to build on each other in order to get to the point that you can tackle something hard. And thinking about it from the perspective of actually training like a person or an entity how to think about these problems requires that same sort of